In this module, we will talk about the receiver operating characteristic, true positive rates, false positive rates, and these three concepts. So to start with, let's consider an experiment where we have two types of outcomes. So for instance, you can label the two outcomes as a positive outcome or a negative outcome. To give you some real world examples, let's look at the following setting. Suppose you receive emails in your inbox. So let's look at the first example of emails in your inbox, which is usually passed to a spam filter, which has two types of outcomes. Either the email is classified as a spam, which we're going to denote as a positive outcome. So positive with respect to a spam, or not spam, which is denoted as a N or a negative outcome. Another example in healthcare is, patient diagnosis, where you go see a physician or a doctor, and the doctor then detects whether this patient has a disease, denoted as a P, or the patient is healthy without a disease, denoted as N. A third example is, for instance, you will submit homeworks, and then a detector can check whether was the homework AI generated, denoted as a P outcome, or a student's original work, denoted as an outcome. Broadly speaking, these kind of problems are also known as binary classification problems, where there are only two outcomes or binary outcomes, 0 or 1, heads or tails, positive or negative. And the key question that we will study in this module is how should we evaluate and measure the performance of such a binary classifier? Okay. All right. So let's think about what kind of outcomes can occur. So we're going to break down the all possible outcomes into four categories. So the first outcome, and let's take the example of spam classification. So the first possible outcome is what we're going to call as a true positive. So let's write down the definition of true positive. And the shorthand will be TP. So true positive corresponds in the spam classification is that suppose your email is indeed a spam. So ground truth is P. And then the classifier, your spam filter, says that email is spam. So classifier says P and email is a spam. Okay, so this is true positive. So the underlying ground truth was positive and the classifier detected it as positive. That's why it's called true positive or TP. You can also define false positive. So what is false positive? Denoted in short as FP. So classifier says spam and email is not a spam, which means ground truth was N, but the classifier said P. Okay. As you can imagine, there are two other possibilities. The third one is true negative. Which means email is not a spam. And then classifier says not spam. So ground truth is N and prediction is also N. And finally, we have false negative. Okay. So N and E. So email is a spam. And then classifier says not spam. So hopefully this is clear. What do these terms actually mean? Okay. Now, in general, the outcome of your classifier could be a probabilistic outcome because depending on what is the content of the email and what kind of mechanism is used by the classifier to make the decision, maybe extracting some specific features of the email, detecting keywords of the email, and then trying to make a decision. In probability terms, we can look at something called a false positive rate, denoted as FPR. So false positive rate. And false positive rate is defined as the probability that your decision is P given that the ground truth is N. Okay, so ground truth was N and you falsely declared it as a positive. That's why it's called false positive. We call it a rate because this is a probability, and FPR is a number between 0 and 1 because this is a probability. Okay. Similarly, we can define true positive rate, TPR. TPR is defined as the probability that decision is P given that the truth is P. Okay. So if you think about intuitively, what would be like a good classifier to possess? So ideally, we wish that your classifier must have true positive rate as high as possible and close to 1. Close to 1 because when the ground truth is P, it better be the case that decision is P with very high probability, with hopefully probability close to 1, right? So we want true positive rate to be as high as possible. And we also want the false positive rate to be small, because this is the mistake that the false positive mistake that the classifier is making. So we want this thing to be small and close to 0. Okay. Now you can imagine we can also define what is, once I tell you FPR and I tell you TPR, you can determine TNR and FNR. Okay, so here's a small fact. So true negative rate and false negative rate. So how can we find true negative rate and false negative rate? So let's think about this. What is true negative rate? True negative rate would be probability decision is N given truth is N, right? So given truth is N, I'm asking what's the probability decision is N? Well, given truth is N, the decision will be either a P decision or an N decision, right? And therefore, this thing should be equal to 1 minus the false positive rate, right? Because condition on the event that truth is N, the decision can be either P or N. These are mutually exclusive events. So these two probabilities should add up to 1. In other words, TNR plus FPR is equal to 1. Similarly, false negative rate is what? Its decision is N given the truth is P. So if you think about the scenario when the ground truth is P, decision can be either P or N. Therefore, FNR must be equal to 1 minus TPR. Okay. So if you want to remember a few things from here, you should remember the following, that TNR plus FPR is always equal to 1, and TPR plus FNR is equal to 1. Okay. So in some sense, there is only 2 degrees of freedom here, because if I tell you FPR and if I tell you TPR, then I can find the other 2 very easily from this box, right? So given all of this, we would like to, what we do when we actually think about binary classification problems, we evaluate them and we sort of visualize the performance in something called a receiver operating characteristic. Okay, so Let's write this down. Receiver operating characteristic, or ROC for short. Okay. So an ROC curve is like, it's a 1/1 size square. On the x-axis, so this goes from 0 to 1, and the y-axis goes from 0 to 1. On the x-axis, we plot a false positive rate, and on the y-axis, we plot the true positive rate. Okay. So if you think about where do we want to be ideally? Ideally, we want false positive rate to be 0, and we want true positive rate to be as high as possible. So this is the point of 0, 1. This is sort of the ideal classifier. Which has 0 false positive rate and 1 true positive rate of 1. Okay. This line, which is the diagonal line, okay, is a random guess line. Okay. So imagine a classifier which doesn't even look at the data that you observe, but always says ground truth, always gives a decision of P. If a classifier always gives a decision of P, then clearly it will it's false. Let's see what will happen if decision is always P. Then the true positive rate will be high, because whenever the ground truth is P, the decision is always P, so true positive rate will be 1, right? However, when the truth is N, it will never make a decision of N. It will always give a decision of P, so false positive rate will be 0, right? So this guy right here and this guy right here correspond to scenarios which are sort of pathological classifiers, which either always give a decision of P or N. This line in between can be obtained by, sort of randomizing your decision. Say you flip a coin with a certain probability and decide whether you want to say P or N, and then you can span all the points on this diagonal line. So this line is also known as the characteristic of random guessing. So this is the random guess line. Okay. In general, we want to be always above this diagonal line. So for example, if I give you a classifier and I measure its false positive rate, let's say I get a point somewhere here. So this is a classifier which is reasonable. Say it's probably better than 0.5, 0.5 somehow. So I would say this is a good classifier, better than random guess. But now somebody else, let's say come tomorrow, designs an even better classifier whose false positive rate is small and whose true positive rate is higher. So this is a better classifier. And then ideally, we would love to sort of go in this direction and hit the ideal classifier as much as possible. Okay. In some sense, the notion of conditional probability. So what I want to emphasize here is all these values, TPR and FPR, these are essentially conditional probabilities. Okay. And what these sort of give us is a sense of how well your binary classifier is performing. Okay. All right. So I want to give you sort of an example building upon this concept of ROC, and I want to show you an ROC curve. What does an ROC curve look like? So what I want to do next is an example of spam filter, some data, and how to building an ROC curve. Okay. So let's take this example. Now, suppose we take a batch of 100 emails. Suppose we have a classifier. Suppose we have a spam classifier. And let's say the spam classifier works as follows, which is going to look at your email. So which reads your email. So reads your email and just counts suspicious words. So it may have maybe a list of suspicious words, and then it says, in your email, so you get this email, and then you check, does this email has how many suspicious words? So it's called S1, S2, dot, dot, dot. Let's say it has, let's say a bank of, I don't know, let's say 30 suspicious words, and then how many suspicious words in this email. And based on that, it can make a decision. So the decision is, you say P, which means spam, or N, which is not spam, if the number of suspicious words is greater than or equal to some threshold, say T. And it says not spam if number of suspicious words is less than this threshold T. Okay, so this is my decision strategy, right? So I want to give you sort of a sense of how to build an ROC curve through this very simple example. Pretty much, this is like a boilerplate that you can take in any binary classification problem. Of course, how the decision is made will be different. It may be done by a neural network. It can be done by a transformer. It can be done by a decision tree. But by and large, you will come up with some kind of statistic. So in this specific example, the statistic is looking at your data. So your data is your email. And then you come up with a statistic by looking at your data. And then you choose, you choose a threshold that if statistic is larger than something, then I'm going to say spam. Statistic is less than that thing, then you say not spam. Okay, so that's sort of the rough pipeline. Okay, so let's see how we can build a ROC curve to understand the performance. Okay, so suppose I have the following type of data available to me and I want to build a ROC curve. Suppose I collect 100 emails, okay, out of which 50 are spam and 50 are not spam. Okay. Out of the spam emails, let's say I have 10 emails with one suspicious word. So I'm going to just write suspicious. Hopefully it's clear. This is what I'm telling you, the statistic. And let's say 15 emails had 2 suspicious words. And then 15 emails here had 3 suspicious words. And then 10 emails had 4 suspicious words. Okay. So this is sort of my data distribution of the 50 spam emails that I recorded. Similarly, for 50 non-spam emails, I had, say, 20 emails with 0 suspicious words, 15 emails with 1 suspicious word, 10 emails with 2 suspicious words, and then 5 emails with 3 suspicious words. Okay. All right. So let's say this is my data distribution, and using this distribution, I want to do something. I want to study TPR and FPR. Okay. So let's think about how we can do this. Let's pick a threshold. So if we pick our threshold as equal to 1. So what do we mean by picking threshold is 1, which means that if I count the number of suspicious words is greater than or equal to 1, then I claim that it is spam. and otherwise it's not spam. So this is my spam classifiers operation or my spam filter. Okay, this is what my spam filter is going to do. Okay. So you can calculate what will be the true positive rate. Okay, so let's try to do that. So for example, let's see this thing. So this is threshold of 1. Threshold of 1. Let's see. So true positive rate. What is true positive rate? It's the number of spams correctly detected divided by the number of spam emails. Given that the ground truth is spam, how many spams were correctly declared as spam, right? That's true positive rate. Okay. So what do you think is true positive rate? How many spam emails do I have? I have 50 spam emails, right? So the denominator is 50. What will this threshold do? It's going to look at every email and detect it as a spam. So how many spams among the spam emails are correctly detected? Among the 50 of them, every single one of them will be detected as a spam because all of these have at least one suspicious word. So my true positive rate is 1. That's very good. Okay. Now what about false positive rate? False positive rate is, remember the definition. What was the definition? That number of non-spam emails which are detected as spam. So number of spams detected, incorrectly detected spams, given that they were actually not spams. So we divide by the number of non-spams. Okay. So how many number of non-spams did we have? We have 50 on this right side, right? Out of which, how many will be detected as spam? Clearly, these 20 had 0 suspicious words, so they will not be detected as spam. But 15 plus 10 plus 5, all these 3 guys will be detected as spam. So what is the count? 15 plus 10 plus 5 is 30. So my false positive rate is 3 by 5, it is 0.6. Okay. So if I choose threshold of 1, then I get a TPR of 1 and FPR of 0.6. Okay. Let's do one more example. Let's say now I increase my threshold to 2. Okay, let's see what happens. If I make threshold equal to 2, then what is my TPR? TPR is out of all spam emails, how many are now detected as spams? Let's go back to this thing. In this case, what's going to happen? I'm only going to declare 15, these 15, these 15, and these 10 as spam. Though these 10 emails will not be declared as spam because they only have one suspicious word, and my threshold is 2 suspicious words, right? So my true positive rate will be 15 plus 15 plus 10 divided by 50, which becomes, this becomes 40 by 50. So this becomes 0.8. And similarly, you can find FPR. FPR will be the number of non-spams that are flagged as spam. So again, denominator is 50. And what will I get? I'm going to only take 10 and 5 and declare them as a spam. Okay, so the upper 20 and 15 batches will not be declared as spam. So I'm going to get 10 plus 5. So I will get 15 by 50 and I'll get 0.3. Okay, so here is the summary so far. So if I threshold of 1, I get this TPR, FPR pair. If I pick threshold of 2, then I get TPR of 0.8 and false positive rate of 0.3. Okay. Now you can do the drill. I'm not going to work every single thing out, but you can imagine if I were to now look at threshold 3, what's going to happen? Threshold 4, what's going to happen? Okay. So threshold is 3. Now we can, I will let you do those calculations, but now we can actually go back to our ROC box. So let me redraw this box. So remember, this was my FPR going from 0 to 1, and this was my TPR going from 0 to 1. Okay. And I can actually plot all of those things. So remember, this was my random guess line. If I pick threshold of 1, so threshold of 1 had TPR of 1 and FPR of 0.6. Where does that fall? That falls somewhere here. So this is say this is threshold is 1. Okay. On the other hand, if I pick threshold of 2, what do I get? My TPR goes down to 0.8. So this becomes, this is 0.8. And this becomes 0.3. This is 0.6. Right? If you choose your threshold, so this is threshold is larger than or equal to 2. This is threshold greater than or equal to 1. And then you can run the thing for others as well. So let's see, what will that be? My numbers are telling me threshold is 0.1 and 0.5. Okay. So somewhere here. So this will be threshold greater than or equal to 3. And then 0 and 0.2. Okay. So if you connect all these dots together, this curve is known as the ROC curve of our classifier, of this binary classifier. How did we obtain this curve? We changed the threshold. We still used the same basic idea of counting suspicious words, but then as we changed the threshold, the performance of the classifier changed in terms of its true positive rate and the false positive rate. And you write down and you sort of show them visually in this plot, and you connect all the dots together, you get the ROC curve. Now, what would be a good ROC curve? A good ROC curve, now once you get this big curve, then you would ask, well, if let's say I have another, classifier and I have two ROC curves, which one should I pick? Now, the way to measure that is something called area under the curve. So AUROC is known as the area under the ROC curve. So basically, this entire area is this area is AUROC. So if you are interested in comparing two classifiers, which one should you pick? Typically, we pick the one which has a higher area under the curve. Remember, if I pick the ideal classifier is sitting here. So if I look at the area under that classifier, that's the entire shaded pink, right? So AUROC, so for ideal classifier, AUROC is 1. So ideally, you would love classifiers to be picked which have higher area under the curve. Okay, so we're going to stop this module.